So we'll have Efrat speak on Steinberg relations for massive products.
Okay, so let me first of all thank the organizers of both events, the Brauer meeting and the QFlex seminar, for the opportunity to speak in the intersection of these activities. So, okay, this is the title, and let me start with the spirit of the meeting here with some Brauer group motivation. For the whole talk, there will be a field F and a positive integer M, and I will always assume that the characteristic is not M. Now, let me assume for the moment, just for this slide, that we have in the field a root of unity of order M, and then we can speak about symbol algebras. So for, actually I have this, so for symbol for field elements A and B, from 0 elements, we have the symbol algebra. So we take two elements, two generators, alpha and beta, where alpha to the M equals A, to the M equals B, and they almost commute up to multiplication by zeta. And then we have the following well-known basic relation that if A is neither 0 nor 1 field element, then the symbol algebra of A and 1 minus A is trivial at the level of the Brauer. Okay, it's somewhat better to think about this in the language of Galois cohomology, so cohomology of absolute Galois group. Let me fix the notation. F bar is algebraic closure. G sub F stands for the absolute group of F. And as always, I will denote by UM the modulo of the Galois modulo of F roots of unity. And then we can speak about the cohomology graded ring, where in degree R, we have half cohomology of the absolute Galois group with cyclotomic action twisted R times with the cup product. Still some well-known things, just to fix the notation. In degree 1, we have the Kummer isomorphism. It's isomorphic to the multiplicative group modulo M, and I denote the if we have a coset on the left-hand side, the coset of A, then I denote by A bracket sub F the Kummer element of A. Now, Tate proved the following fundamental, it's called Steinberg relations for historical reasons. If A is neither 0 nor 1, then the cut product of the Kummer element of A and H2. So I guess it is here well known, but we say it anyway, that this led to wonderful developments related to the normal residual homomorphism. Yes, we have a homomorphism of graded rings, where the target group is our cohomology graded ring, and the domain is the Milnor K ring. So we take the tensor algebra of F cross and divide it, because of Tate's relations, we can divide it by the pure tensors of elements A, because this is killed by M. So the map sends a pure tensor to the cup product of the Kummer elements. Okay, so the main result here is the Voivodsky theorem. This is an isomorphism, which is basically everything that you want to know, because it gives you a complete elementary description of this cohomology ring, just as the tensor algebra modulo a few simple things. So in some sense, this is the end of the area, because what else can you ask? But still, in recent years, in the past decade, I would say, there has also been a lot of interest in this cohomology ring, but not just as a graded ring with the cup product, but also there are some external operations on this ring that go beyond the cup product, the external cohomology operations. in particular, what is called massive products. And this is what I would like to talk about to relate the Vogt-Ross theorem to massive products. Okay, so what do I mean by this? External cohomology operations. From now on, I will assume that our field contains the roots of unity of order M. It's not really needed for the results, but it will, simplify the presentation. So forgive me for that. And then our cohomology ring looks much simpler. We have just the trivial action on C mod M. Now, for the massive products, we take a profinite group G, and for n, an integer at least, we have the n-fold massive product. What's that? It's usually written like this with triangular brackets. So it's from the direct product of n copies of H1 to H2, but I'm a little cheating here. It's not really a map. It's a multi-valued map. That is, if you take the massive product of n elements here, it is not an element of H2, but a subset of H2, which sometimes is even empty. In the special case where n equals 2, this set consists exactly of the cup product. So you can think about massive product as a very big generalization of the cup product structure in this homology. I should say that one can define massive products in more generality in the homological context of differential gradient. I'm interested only in group cohomology in H1 and H2. It is in the language of group extension. In fact, for people in the conference, it appeared yesterday in the very nice talk by Tamar Baron. It goes like this. First, we look at the group, which I denote by UN, all unipotent upper triangular square matrices of size n+1 on n+1. Here I take it over the ring C mod M. So things like that, I hope you can see it, it's a little small. So you have ones on the diagonal, you have zeros below the diagonal, and arbitrary elements from Z mod M above the diagonal. So that's a group. And next to it, we look at the group which I denote by UN bar. So all such matrices, but n+1, and you simply delete it. So things like that. I put here a dash for an entry that you delete. Okay, so this also turns out to be a group. You just ignore what happens here, and 0 times anything is 0. And what we get here, maybe I can move this thing a little bit. Okay, well, not really. So what you get here is central extension. From UN, you project into the partial matrices, and the kernel is just Z mod M. Okay, now for the definition of the massive product. Again, we take a profinite group G, and we also take a continuous homomorphism rho bar from G to the punctured matrices, UN bar. So it goes like this, it's vertical. And here below, I wrote the extension from the previous slide. Now, we can take the it looks like this. So here on the right, we have G, the kernel is Z mod M, and in the middle, we have the five products. So the same thing in UN bar. Okay, central extensions correspond to elements in the second cohomology. Let's start with the lower extension, M. of U and pullback extension corresponds to the cohomological pullback of and apply to it the functorial map rho bar star. So rho bar star is the map from H2 of U bar to G represents. Now take n elements in the first cohomology. Because the action here is trivial, these are just continuous homomorphisms from G to Z mod n. So their massive product, oh, that's not good, this little square here. This is the right. Okay. Their massive product is the set of all such pullbacks. So if you wish, all such central extensions, cohomologically, the rho bar ranges over all such homomorphisms such that, well, rho bar is into matrices. So you look at what happens at the super diagonal, so at entries I plus 1. And you want that on the super diagonal, the entries will be phi 1, phi 2, and so on. And then you collect all these elements. Okay. When is this non-empty? It's non-empty precisely when you have such a homomorphism with the phi i's on the super diagonal. So a homomorphism into the punctured matrices. It's also important to know when does this set contain 0. Okay, it contains 0 if you have such a pullback extension, which is trivial, which means that it splits. The massive product more as feature row, have a homomorphism from G to the full UN with super diagonal being phi 1, phi 2, and so on. Okay, let's remember this fact. It will be important in a moment. And now let's go back to the standard relation to the case. Let's go for field element, which is neither 0 nor 1. The cut product of the Kummer element of A and the Kummer element of 1 minus A is 0 in H2. Okay. Now we can translate this into the language of massive products. Yes, we take the twofold massive product, which is the set consisting just of the cup product. So here is that 0 is contained in this twofold massive product, right? Because of the last remark from the previous slide, it means that there is a homomorphism, continuous homomorphism, the group into two Kummer elements of A and 1 minus A. And here I don't care what, some continuous map, making the whole thing a homomorphism. Okay, but when you put this in this way, it really calls for generalizations. What happens if you take not U2, but higher UNs and put on the super diagonal some other more complicated lists of Kummer elements? So what generalizations can we have? Okay, we can have generalizations. So here I take n to be at least 3. And I need to assume that and also that the characteristic is prime to n. Okay, the first result in this direction is due to Kirsten Wickelgren from a decade ago. She considered this massive product. So all elements here are the Kummer elements of A, and at exactly one point you have the Kummer element of 1 minus A. And she proved that this contains 0. In the language of homomorphism, what it means is that there is a homomorphism from GF, the absolute Galois loop, to UN, where on the super diagonal you have the Kummer elements as in this list. So A, then suddenly 1 minus A, and then again A. There is such a homomorphism. She also proved another result in the same spirit a few years later. Here she took on the left and on the right the Kummer element of 1 minus A, and in the middle many A's. She first proved that this is non-empty, which means that you have a continuous homomorphism. Now it's from the absolute group to the punctured matrices. So U and bar, this is what means non-empty massive product. And here on the super diagonal, you see you have all these Kummer elements as in her list. I should say that she also proved that this contains 0, but this was by some additional argument that I will not need here. Okay, what happens if we take general Kummer elements of A and A? So this is the main result of the talk. So theorem. For every list of length n of Kummer elements of A and 1 minus A, so any multiplicity, there is a continuous homomorphism from the absolute Galois group to U with this list on the super diagonal. Now, by here deleting entries near the upper right corner. What's that? Maybe you do not delete anything, you take the full UN. Maybe you only delete the upper right entry. You get U and bar. But sometimes you need to delete more entries. Depends on the person, on the list of the Kummer elements that you have here in a so you have here partial matrices, partial in the sense that you erase some stuff next to, in the area of the upper right corner. Okay, let me be more precise now. Well, it's convenient to encode your list by a word, use W of n letters, Z1 to Zn. There are letters in the alphabet, X, Y, two letters, where X means that you have displaced the Kummer element of A, and Y means that you have displaced the Kummer element of 1 minus A. And now, an important definition. T is a set of entries in the upper right triangle. Which entries? All entries ij, I is less of j, take the segment of the word W that starts with Zi and ends just before Zj. So it ends at Zj minus 1. You look at this segment and ask whether it consists only of x's with possibly one exception, which is y. If it is, then you put it in T. If it isn't, then you don't put it in T. Now, UT, the group in the main theorem, is the group of all partial matrices with this set. So all unipotent upper triangular partial matrices where you take only entries here. Here, I guess I must give some examples. So here are some examples. So just, okay. Let's make this concrete. Consider this word, 5 letters, YXX, YY. And I claim that here the group looks like this. So stars mean entries that you do take, dashes mean entries that you delete. Why? For example, maybe here I should try to write at home. I hope I can make it. Just one moment. So, for example, if you look at this entry. So this is entry 1, 5, which means that you start with the first letter and before the 5 letters, the 5th letter, you have y, x, x, y. In this segment, you have 2 y's, so you must delete it. Or if you take this place, entry 1, 6, which means that you take the whole word. The whole word, it has 3 y's, you certainly must delete it. Or, for example, take this one. This one is what? It's 4, 6, which means that you take this part, y and y. 2 y's, you must delete it. Or here, which is okay, 1 y is allowed. Okay, so where was that? Or a very simple example. You take a word which is only x, 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 no matter what you do, you don't have y's, so you don't delete anything, you get the full un. Or if you take a word which has only 1 y, again, everything is allowed, you don't need to delete anything, so you get the un. Now, you see, this is the first situation considered by Wickelgren. It corresponds to the list, the Kummer element of A, then 1 minus A, and then X. And indeed, you get the full UN. The second situation, due to Wickelgren, is that when you take Y and Y on the sides, and in the middle you have X's, the only way to take the whole word, which means that you are in the upper right corner. So you only delete the upper right corner, right? So what you get is UN bar. So these are some examples. Let's just one remark. If you look at example 1, then it's very clear here that the stars are, so to speak, convex towards the diagonal, which is quite clear. I mean, if you have a segment with at most 1 y and you take a smaller segment, you still have at most diagonal. This is very important because this makes it a group. Because of this, you can multiply such matrices the same way that you multiply the Yes, yes, it's the multiplication in UN induces a group structure. Okay? So,
did you say in situation 4 that she proves that you can take UN? Is that what you said?
Well, she has an additional argument that allows one to get that also 0 is included in the massive product, but for us, have this. This is what we actually do. If I have time, I'll say more about this point. Okay, so this is the result, and at the remaining time, I'd like to try to prove.
What happens with symmetry between A 1 minus?
Okay, the question is what happens with the symmetry between A and B? In fact, we do get here 2 homomorphisms for 2 groups, T that corresponds to X and Y. Yeah, exactly. So, the basic idea of the proof, and I should stress that it's basically it's based, which is a combination of geometric methods and algebraic and combinatoric methods. But at some crucial point, we add a certain legal structure enables us to generalize it to our with. Let me know by C the formation of all finite groups of order prior to the characteristic and to n factorial. So by our assumptions, Z mod n is such a group. And okay, we can, as usual, speak about pro-C groups. Let chi be the Procy cyclotomic character from the absolute gamma group. Click at this group, rolls the Galois action. Now comes the geometry. Let x be the projected line minus 3 points, 0, 1, infinity, and of x extended by scalars to this base point, and here it is a tangential base point from 0 to 1, whatever this means. I will not speak about this. And then you take the Procy completion and call it Z. Now, if you're not familiar with this stuff, never mind. There will be just 2 or 3 facts that we will need, algebraic facts that I will state very precisely and clearly. It's not as complicated as so one fact that we need is that there is a natural Galois action, the absolute Galois group acts on S. In fact, the structure of S and the Galois action are very well known by works of prominent mathematicians, Hara, Delin, others. S, this fundamental group, turns out to be just a free Procy group on 2 generators. I call them deliberately X and Y as the letters in the alphabet. What is the Galois action? It's also very simple. Taken out, it acts on the generator X just by profinite exponentiation by the cyclotomic character. The action on Y is slightly, not too much, slightly more complicated. Sigma acts on Y by first exponentiation by the character, but then we conjugate an element which I call F sigma. What's that? F is a continuous one cocycle from the L group to the power by some component. Okay, find 3 homomorphisms. The first 2 are very simple. Delta X and delta Y are from to them. It's enough for them to Y. So they are basically, Kronecker maps the generator X Y and the generator Y to 0. Delta Y does it the other way around. Okay, Kronecker delta. And it's not hard to check. Galois variants, they are compatible with the action of the absolute Galois group. Also, let me the absolute Galois group acts 3 group partial matrices UT. Now, the first main step, or the biggest step in the proof, step 1, is to construct a map 5 bar from our fundamental group, from this 3 Procy group to generate X into the group partial matrices with 3 properties. It needs homomorphism, it needs to be Galois invariant. These triangles, if you look at some entry on the superdiagonal, it's like taking delta Zi. Zi was the letter in the word that tells us whether we take the Kummer element of A or of 1 minus A. Okay, suppose that we have it, and everything is, which means that all these homomorphisms induce homomorphisms on a star. So delta X lower star, delta Y lower star are from the cohomology of X to the cohomology of Z mod N. And induces the homomorphism from cohomology of S to the cohomology of the same triangle, commutative triangle. Now the second step, this is entirely due to Wickelgren, here I added nothing, I should say. One should look at rational base points of X, which means either every element neither 0 nor 1, or tangent base points. And for every such rational base point, there is a canonical construction, the Kummer map from the base points first cohomology of S, with the property. Let me now plug in the triangle. If you take an F rational point here, so A is a field element which is neither 0 nor 1, and you go first to H1 of S and then go down by the delta to H1 of Z mod N. She calculates that what you get is the Kummer element. So if you go down by delta X, what you get is the Kummer element of 1 minus. Okay, but you can take another route. You can go up here on the upper row. This H1 of the absolute Galois group acting on UT trivially is just homomorphism. So A down the edge of a row lands you here, which gives you a continuous homomorphism from the absolute Galois group to UT. Now, if you look what happens to the elements of A and 1 minus A precisely in the order that you want. So this is what we want to prove. All that remains is to construct this homomorphism phi bar W. If all it's, how do we construct it? It will come in several steps. Structure. Suppose that you have a set of integers between 1 to n. And you have a positive integer. Okay? All entries, again in the upper right triangle, with this satisfied. Okay, I should be less equal J. Now, if you take the interest between I and J minus 1, it should contain a small number of points. So the calculated intersection should be smaller than S. So we said let V S be the kernel of the natural projection from the full UN to the group of partial matrices, partial in the sense that you only take these entries. So what it actually means is that you take entries, or that you take matrices in UN, which are 0 if you are non-diagonal entries in this set. So a matrix here looks like this. On the diagonal you have ones, then near the diagonal you have general elements. So what we get here is a filtration of UN, one, so on, it becomes smaller and smaller. The N1 is always 1. Now the key point by which we take this improvement is that this filtration behaves nicely. For example, the commutator of Vs and Vt is in Vs plus T. And if you take an nth power of something in Vs, then you land in filtration. It's closely related to the Zassenhaus filtration of UN. So what we actually have here is a graded V algebra where in degree S, we take this commutative group Vs modulus Vs plus 1. So this is the additional structure that one which set Z of integers do we take. So the next step, and let me remind that W was the word Z1 to Zn, the letters are X and Y, and you take Z to be one of the following. I ZWX, which is all places Zi is not X, in our case, larger alphabets, I prefer this notation, or ZWY, all places where Zi is not Y, which means that it's X. Okay? And then, this is the key definition. We apply the construction from the previous slide, these sets. With respect to the first one, WX, we get a set of entries in the upper right triangle, TXS. What's that? All entries, IJ, in the upper right triangle, such that when you take the segment of the word starting with ZI and ending just before ZJ, the letter Y appears a small number of times, less than S times. Now, let me for I and J such that this segment contains Y at most once. So we actually considered TX2. Okay. So we can also make the same definition with X and Y interchanged, and we get here two filtrations of UN. So one filtration corresponds to these sets, VX1, VX2, and so on, and the other is VY1, VY. The last part of the construction. First, if you have a letter Z, which is X or Y, let me write RZ for the following operator. You take usual angular matrix. You replace the entries outside TZ1, but so if you are in TZ1, you get this. Outside TZ1, you have to check that this is a homomorphism. Now the definition. The homomorphism phi double from S to N. You do the following. First, for some reason that I will not have time to deal with here, you take this matrix that on the diagonals above the main one, you take inverses of factorials. There's not much place to play. So yes, there is an exponent. So yeah. So you replace everything outside TX1 by 0. Y goes to the same thing, but you replace other entries by 0. Entries outside TY1. And okay, this was a homomorphism into UN. I want a homomorphism into partial matrices. So we just project. We forget what happens outside. So this is our one example. The same word that we had before, Y, X, X, Y, Y. What do we do? First X, phi W of X, this is over to factorial because we are on the second diagonal of the main one, but we replaced many such fractions by zeros, everything outside TX1. And for Y goes to this, so we replaced other entries by zeros. And then we need to project, we need to go to partial matrices, that is, forget what? Forget these entries, these entries. So this is what you get for this word. It's very explicit, but it's quite complicated. Now, I think we started a few minutes
You can take some more.
Oh, okay. So we need to verify the properties of phi bar W. Which properties? We need to know that we have these commutative triangles that on the diagonal, what this homomorphism is the Kronecker deltas. And we need to verify equivalence, Galois equivalence. One is very simple, as long as one remembers the definitions. But what happens here, we verify this on the generators, x, y, of S. For example, on X, what happens here that I applied phi bar W and then took a super diagonal entry. It means that we have first 1 over 1 factorial. If you are in Tx1, you keep it. You are not that you have 1 or 0, depending on whether Zi is X or Zi is not X, which is exactly our Kronecker delta, delta I, you apply. So 1 is very common. What about the equivariance? So now it's almost the last slide. Well, the first thing one should note is that Tx1 and Ty1, the intersection is the because if you have a segment that has no x's and no y's, then it's the empty segment, which means that you are on of x. So this matrix, and you make it 0 outside Tx1. If you are in Ty1, and not if you are not T1, this exactly means that you are in the first group of the filtration corresponding to 1. In the same way, phi W of y is in Vx1. Now, these two, that the commutator is in both normal subgroups. Also, as this fundamental group or commutator subgroup is generated as a normal subgroup by the commutator of x and y, which means that image phi W commutator is the action of an automorphism in the absolute W on Y. Remind, it was like this. We took exponentiation by the cyclotomic character and then conjugation by some commutator. Okay, we applied phi W. Phi W of Y was here. So it's on the upper right, the second line. It's in V1x. F is a commutator, so phi W of F is also in V1x. So we get here a commutator, now enters the structure. It is in 2x. It is in V2x, which means that V2x, these two images of phi W. Let's look at phi W of this conjugate and phi W of y to the power of the cyclotomic exponent. We get, we deduce they coincide modulo V. Now, last line here, what are these things? Well, the first one is phi W of the action of y. Here it's a little computation because the roots of unit field, the cyclotomic character is 1 plus, it doesn't really matter that you took here this exponent, you get phi W y, means that they coincide exactly on the entries that we did. So this is the variance on y, and equivariance on x is even simpler because we don't have this conjugation, so it's even quicker. So I'll skip this slide, and thus, because of these computations, phi bar W is gamma equivariant as we wanted to show. Let me finish with one question. So it's actually a very vague question, but I hesitated and I should state it here, but I think I should. We started the whole story with the classical relations due to tape that led to the construction of the Milwaukee ring and led to the formulation of the norm reciprocal theorem, and it's proved by Voivodsky and Rost. Now we have other kinds of Steinberg relations related to these external cohomology operations, massive products. So I wonder whether the Voivodsky-Rost theorem can generalize in some, I wrote here, Massey-like relations, these pullbacks or these homomorphisms. So this is very vague in the sense that we still need a formalism to state it. Yes, in the classical situation, one defined the Milwaukee ring. So what is the analog of the Milwaukee ring for these homomorphisms? So we need a formalism, we need a conjecture, and then we need also to prove this conjecture. So I think it's the vaguest thing I've ever said in a talk in my life, but I believe that this is a question worth asking. So thank you.
Question? You have some sense as to how far this is typically being optimal, because you said in one case you need to remove upright entry.
Well, so I should repeat the question. Expectations into larger groups of matrices. Well, there is a conjecture. It's called the strong Massey vanishing conjecture, which predicts that if you can go to the super diagonal and the diagonal above it, then you can go all the way to UN. But the conjecture does not say how to do it. So we should accept, but the conjecture is not explicit. Here, everything was explicit.
From an algebraic course perspective, T is an integer partition, and when you remove it, it's a substitution, well, a reverse substitution, and those 1 over factorials are almost book length. The
Most
book length from the book length formula. And there are very good algebraic combinatorial generalization of those things with plane partitions instead of integer partitions. You analyze this kind of and
okay. So that's something I will be happy to discuss with you later.
So the assumption that P incarnates is made of factorial n.
Okay, the question is whether the assumption about the characteristic being prime to n factorial, it can't be removed, unfortunately, in this method. Well,
what you need is factorials because from GA to something.
I think that it's possible to get rid of it.
It shouldn't be an hypothesis. And that's the one. So
That would be great if we are able to move this. I mean, this was an obstacle also in the works by Winkelgren. Right, because even for the classical state relations, they hold also for the prime number 2.
Questions?
But we have